ঠিক আছে, তাহলে শুরু করছি। So in this case, you see, the situation will remain same if we extend the surfaces ideally up to infinity. If we go on extending the surface in this direction or in this direction, or if we go on increasing the magnitude of the push, the ball will always be able to regain its initial position or initial state of the motion, which was zero state. Because the velocity was zero and the displacement was zero. So this state, the initial motion or the initial state or this particular state will always be regained by this particular system. So automatically we can say that the system is stable. System is stable, and we use another term that is or we use two terms to define the uh, nature of stability of the system, and the terms are কোথাও একটা লেখা আছে আমি খুঁজে পাচ্ছি না, yes এখানে. So the terms are globally asymptotically stable. So what is meant by asymptotically stable? Let's go to the figure once again. You see, whatever be the magnitude of the push and whatever be the length of the surfaces in both the direction, the system, as I said, the system will always be able to regain its initial state of motion. So it will always come to this zero state. So if a system always, in the absence of the input, if we remove the disturbing input, if you remove the disturbance from the system, and if the system regains its initial position of the motion, then the system is said to be asymptotically stable. The system is asymptotically coming to the zero state. Hence the term asymptotically stable. Now let's go to discuss another surface where the nature of the surface is like this, right? Again, a ball is resting at this particular point, as you can see, and since the ball is at rest, hence the velocity and the displacement of the ball with respect to this reference position will again be zero. Now if you disturb the ball, that means if we give some disturbance, that means if we push the ball either in this direction or in this direction. So look at this region denoted by this dotted lines. So within this region, if the ball moves within this particular region, again, just like the first case, it will exhibit damped oscillations like this about this in position or zero position, and finally it will be able to regain its initial zero state of motion, right? But if the push is pretty hard or harder one, and if the ball crosses either this ridge in this direction or this ridge in this direction, then what will happen? The ball will start rolling down the surfaces in this direction or in this direction, right? And the ball will never be able to regain its initial state of motion, which was zero state, right? So the ball is stable within this region only, or the system is stable within this region only. So to differentiate between these two situations, the first case and this case, this situation is called, or this stability, the nature of the stability of the system is depicted by the term locally, again asymptotically. Why? Because when the system is locally stable, it will be asymptotically stable. তাই তো?
Yes, ma'am.
বোঝা যাচ্ছে কি বলছি?
Ma'am.
So locally asymptotically stable. So in contrast, you see, this situation can be depicted as globally asymptotically stable. globally asymptotically stable, right? Now, the second case in this is basically the nature of the surface, nature of the trough. And suppose we have managed to place a ball, somehow we have managed to place a ball at this particular point, at this particular point. So now if we give a gentle push, a very gentle push to the ball, what will happen? The ball will roll down along this axis or, along the surface or along this surface, and the ball will never be able to regain its initial zero state where the velocity and the displacement were zero. So the system is unstable. The system is unstable. Remind me, I'll come to this term equilibrium state. And the fourth surface is like that. This, a flat surface, and obviously friction is there. So suppose this was the initial position of the ball, and this is the reference position, and at this point the velocity of the ball was zero and the displacement of the ball is zero. Now if we give a push to the ball, suppose in this particular direction, we can push the ball in this direction as well. So what will happen? The ball will start rolling along this particular surface, and because of the presence of the friction, the ball will stop somewhere at a position B, where again the velocity, this physical quantity, the velocity of the ball will be zero, but the displacement is not zero. The displacement is not zero because the position B is not identical to the position A. So the ball is not actually regaining, the ball is stopping, but the ball is not actually regaining its initial position of motion, right? So it cannot go back to its initial zero state. And hence, the nature of stability of this system is, we can say the system is stable, but the system is non-asymptotically stable. Yeah, it's here. The system is non-asymptotically stable, right? And this zero state, all the zero states are basically known as equilibrium point or equilibrium state. It's written over here. So let's go through the lines. So if we remove the disturbing force, the ball exhibits a damped, that is the first case, due to the friction of the surface, damped oscillatory motion about the point of rest or the point of equilibrium, or in other words, the equilibrium point. So what is an equilibrium point? An equilibrium point is a point or an equilibrium state. An equilibrium state is a state where a system remains for all time t greater than equal to 0 unless it's disturbed. So should I repeat?
Yes, ma'am.
So what is an equilibrium point? An equilibrium point or an equilibrium state of motion of a system, since we are considering a dynamic system, we can say the state of motion. Equilibrium state of motion means the system will remain at that particular point or exhibit that particular state of motion for all time t greater than equal to 0. That means it will remain at that particular point, forever, unless it's disturbed. So look at this particular figure. Unless you disturb the ball will remain at this particular position forever. It will not change its position. It cannot change its position. So that's why this is known as equilibrium point. Equilibrium point. And why the system is stable? Because even if we disturb the system can come back to its equilibrium point or equilibrium state of motion. That's why the system is said to be a stable one. Whereas in the second case, since the system cannot regain its initial state of motion or initial uh, point, hence the system is said to be an unstable one. বোঝা গেছে লেখা হয়েছে?
Yes, ma'am.
Yes, ma'am.
Our next topic is concept of stability and algebraic criteria. So as I said, in this particular course, we'll be discussing only linear time invariant system. আচ্ছা তোমাদের কি অন্য পার্টটা শুরু হয়েছে?
No, ma'am.
No.
No, ma'am.
Ma'am, notes দিয়েছেন ma'am.
আচ্ছা আচ্ছা ঠিক আছে। না আসলে আমার পার্টটা একটু মাঝখান থেকে একটু অ্যাব্রাপ্ট ওয়েতে শুরু হয়। এনিওয়ে ঠিক আছে।
ম্যাম নোটস পাঠিয়েছেন।
পড়েছে।
ম্যাম নোটস পাঠিয়েছেন আর বলেছেন যে নোটস পড়ে যদি কোনো প্রবলেম হয় বা ক্লাস অ্যারেঞ্জ করতে হয় তাহলে ম্যামকে বলতে।
আচ্ছা ঠিক আছে। যাকে তোমরা তো সিস্টেম থিওরি পড়ে এসছো, জানো এগুলো। Linear time invariant system. So what is our basic considerations? The first consideration is we are considering a linear time invariant system which is either in a quiescent or zero state. State এখানে লেখা নেই। In a quiescent or zero state. State-টা কোনো রকমের pen through হয়ে গেছে, যাই হোক। Quiescent state means zero state of motion. That means the system is at equilibrium state or exhibiting dynamic C0T. This is zero. C0T due to the action of an impressed force, right? So if there is no force, then the system will be a free system. The system is called a free system, and it might so happen the system will not exhibit any motion. So the system will remain in its quiescent state, zero state, right? And if we apply some force, then what can happen? The system can exhibit some dynamic motion. Okay. And that particular the system is exhibiting some kind of dynamic motion or the system is in the quiescent state. That means system is showing or generating some output. That particular output is denoted by this term C0T. C0T. Okay. Now let's assume that we are applying a disturbing force. We are disturbing that particular system which was lying, which was previously in its quiescent state. And the nature of the disturbing force is like this, a state. And the state was applied at a time t is equal to minus t1, where t1 greater than 0. That means the step has been applied, the disturbing signal or disturbing input has been applied at this particular time, and it was working on the system at time t equal to 0, the disturbing signal or disturbing input, the second input, the disturbing input is being removed from the system, right? Now we'll try to observe the output of the system for time t greater than t0 greater than equal to t0 plus. Clear?
Yes, ma'am.
Now, because of this disturbing force, the system will exhibit an output only because of this disturbing force. The system will exhibit an output which is equal to CDT. CDT. right? Now, since the system is a linear system, it obeys the property of superposition, law of superposition, right? So when both the forces are acting on the system, or the disturbing input was impressed upon the system, and then if we want to find out the resulting or the equivalent output from the system for t time greater than t0 plus, that means the output of the system, the resultant output of the system will be additive sum of these two outputs, C0t and CDT, since the system is a linear one. বোঝা গেল?
Yes, ma'am.
So what we'll try to find out? We'll try to find out CT. CT is the resultant output exhibited by the system because of the input and because of the disturbing force applied on the system. So the output will be C0t plus CDT. Now we are trying to find out what happens to CT, output of the system, as t tends to infinity. T tends to infinity. So that means we are trying to find an answer to this question, limit t tends to infinity, C0t plus CDT, what happens to that? Now this equation can be rewritten in this form. So we are trying to find out what happens to CDT, that means the response of the system, output and response, these two terms can be used synonymously. So what happens to the response of the system because of the impressed disturbing force? And the disturbing force has been defined in the previous diagram. So what happens to CDT as t tends to infinity? That means this will be equal to limit t tends to infinity CT minus C0t. CT minus C0t. What happens to that? You see, if as t tends to infinity, CDT decreases to 0. CDT decreases to 0. That means with time, the output of the system, becomes same as the output of the response of the system that was being exhibited by the system without the disturbing force, isn't it?
Yes, ma'am.
So under that particular situation, we can say even if we disturb the system, then also as time progresses, the output of the system doesn't deviate farther and farther from the original output. And that was the basic concept of stability, right? Now, there could be three possibilities. What are the possibilities? The first thing is t tends to infinity, limit t tends to infinity, CDT could be 0. That means as time progresses, time advances, CT will be equal to C0t. That means the original output, actual output of the system, initial response is same as the final response after the withdrawal of the disturbing force. The second condition could be that as t tends to infinity, CDT will be infinity. That means will go on increasing farther and farther. That means plus minus infinity or sustained oscillation with infinite amplitude. Either it will go on increasing like this or sustained oscillation with increasing amplitude. And the amplitude of the sustained oscillation will go on increasing towards infinity, or combination of both of this, right? So obviously this situation is not a desirable one. Okay, and what will happen? finally the output of the system, even after the removal of the disturbing force, will go on increasing towards infinity. That means the output of the system will be unbounded, though the input to the system was bounded. Output of the system will be completely unbounded. That means completely uncontrollable, right? So naturally, we cannot work with that particular system. Or there is a third possibility that as time increases, the disturbing force, the response due to the disturbing force will become constant on finite magnitude. That means it will be something like that, a DC sort of signal at the output, or OT, oscillation with finite amplitude, oscillation with finite amplitude, or combination of these two. Combination of these two. So this could be the three possibilities. Is there any other possibility? আর কিছু হতে পারে, জিরো হতে পারে, ইনফিনিটি হতে পারে, অথবা কনস্ট্যান্ট হতে পারে। আর কোনো পসিবিলিটি আছে? নেই তো?
No.
So obviously, this situation is pretty straightforward. So under this particular condition, the system is stable. The second situation is also quite obvious. The system is unstable, right? And the third situation is interesting enough. You see, the response of the system due to the disturbing force, even after the removal of the disturbing force, is not dying or decaying down to zero. Instead, it's becoming either constant amplitude, or it's becoming a constant oscillation with finite amplitude, etc. Okay, so directly we cannot classify this particular system as a stable one or an unstable one. So if you can allow this much of amplitude, constant amplitude, if you can tolerate this much of constant amplitude at the output of the system, that means you can work with that particular system. Or if you can allow this much of oscillation with finite amplitude at the output of the system, right? So in that case, you can work with that particular system. That is true for this case also, right? So under that particular situation, we can work with that particular system. So that means we'll treat the system as a stable one. But if we can't allow, if the magnitude is significantly large, or the amplitude of the oscillation is significantly large, and if we can't tolerate that amount, that much of deviation at the output, then we cannot work with that particular system, right? So under that particular situation, the system will be treated as an unstable one, right? So in general, this situation, if a system exhibits this kind of a situation, then the system will be in general called, আবার বোধহয় সেশন অফ হয়ে যাবে নাকি, limitedly stable. Limitedly stable, right? So the first one was a stable situation.
সেশন এখনো 10
Step-
মিনিট আছে।
10 মিনিট আছে। আচ্ছা, আজকে যদি সেশনটা অফ হয়ে যায়, তাহলে আজকে আর রিশিডিউল করব না। তোমরা
আচ্ছা।
নেক্সট কবে ক্লাস করবে বলো, তারপরে তোমরাই যদি গুগল মিট থেকে হোস্ট
হ্যাঁ,
করো
আমরা
তাহলে আমার
লিংক
খুব
পাঠিয়ে
সুবিধা
দেবো।
হয়। কারণ আমাকে মেয়েকে ধরে এসব করাতে হয়, মেয়ে খুব বকে।
ঠিক আছে ম্যাম, নো প্রবলেম।
Achha. Stable, if the response of the system to a bounded disturbing force vanishes, ultimately at t tends to infinity, the system will be called a stable one. And if that is not the case, that means if the response of the system to a bounded disturbing force ultimately becomes an infinite amplitude, which means unbounded, or an oscillation of infinite amplitude, or both, then the system will be treated as an unstable one. Obviously, the system will be an unstable one. System is an unstable one. And limitedly stable means, in this case, the response to a bounded disturbance ultimately becomes a constant or a constant amplitude oscillation, or both. So if we can allow that much of deviation in the output, the system will be treated as a stable one, otherwise the system will be treated as an unstable one. Now, এটা বোধহয় তোমরা পড়েছো, বিভো স্টেবিলিটি, অ্যাসিম্পটোটিক স্টেবিলিটি পড়েছো কি তোমরা?
বিভো স্টেবিলিটি পড়েছি।
So বিভো stability stands for bounded input, bounded output stability. So as I said, if the input to the system is a bounded one, then for a stable system, the output has to be bounded. The output cannot be unbounded. And if the input to the system is bounded and the output of the system is unbounded, obviously the system is not stable, right? So this notion of stability is, if an input is bounded, then for a stable system the output will be bounded. This notion of stability is known as bounded input, bounded output stability. And what is asymptotic stability? Bounded input, bounded output stability, or this notion of stability is applicable for a forced system. What is a forced system? Where you have given some input. Bounded input, that means you have given one input. There is some input acting on the system. So if there is an input, the system will be called a forced system. And if there is no input, then the system that the system, a dynamic system, can exhibit its dynamic behavior because of its initial conditions, right? If we change the initial conditions, then its response will change. So if there is no input to the system and the system is exhibiting dynamic behavior because of its initial conditions, then the system is called a free system. No input is there. And in case of a free system, the system will always, a stable free system will always be able to regain its equilibrium point or zero state of motion. So that particular notion of stability is known as asymptotic stability. Already we have discussed that. Asymptotically stable. Let's go back. Let's come back to this particular figure. That was the initial condition. So in that is the equilibrium point as well. This is the one single equilibrium point for this particular system. For a linear system, only one equilibrium point exists. But for a nonlinear system, multiple equilibrium points may exist. Anyway, so if I change the initial condition, instead of placing the ball at this point, if I place the ball at this point, then its motion, its path will be a bit different, but finally it will come to this particular position, isn't it? I'm not disturbing the ball. I'm not giving any disturbing input. Just instead of putting the ball over here, I'm placing the ball at this point, and it will exhibit again a different type of trajectory, but will finally come to this particular point. So the system will be exhibiting its dynamic behavior because of its initial condition. There is no input, and the equilibrium point will be regained. So this notion of stability is known as asymptotic stability, right? And in case of a linear system, if a system is BIBO stable, then the system will be asymptotically stable, or vice versa. That means if the system is asymptotically stable, then the system will also be, if you impress one input, under the input, the system will exhibit a stable response. So for a linear system, If a system is Bibo stable, the system will be asymptotically stable, or if the system is asymptotically stable, the system will be Bibo stable.
Excuse me, ma'am.
Bolo.
Ma'am, can we say that initial state of a system is its equilibrium state?
No, 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 no. As I said, just let's come back to this particular example. As I said, if I place the ball at this particular position, when v is equal to 0, d is equal to 0. This is the only equilibrium point. This is the only equilibrium point. You see, what was the definition of the equilibrium point? The system can stay at this particular point forever if you don't disturb the system, right? But if you place the ball over here, it can't stay at this point forever. It will come back to this point. So this is the only equilibrium point where the velocity and the displacement was 0. And that is the initial, those were the initial conditions. Instead, if I place the ball over here, neither the velocity nor the displacement will be 0, isn't it? But the velocity at this particular point, some v dash, and the displacement at this point with respect to this equilibrium point will be the initial conditions. And because of this initial conditions, the trajectory of the ball exhibited, the trajectory exhibited or described by the ball will be a different one. Even if you don't disturb the ball, if you even don't push the ball will start its motion and finally will come to this position of rest, which is the equilibrium point. Am I clear? If you place the ball at this particular point, so the velocity and the displacement of this particular point will describe the initial condition. And then the ball will again describe a different trajectory. But as time t increases, it will come to rest at this particular point, which is the sole equilibrium point for this particular system. Again, I am repeating, for a linear system, always there will be a single equilibrium point. দেখো এবার বোঝা গেল কিনা initial condition আর equilibrium point এর difference.
Yes.
কে জিজ্ঞেস করেছিল, is it clear?
Yes, ma'am. Yes, ma'am.
Absolutely clear?
Yes, ma'am.
আচ্ছা, কত টাইম বাকি আছে?
1 minute.
Yes, ma'am.
ঠিক আছে, তাহলে আমরা আজকের সেশনটা আর কোনো কোয়েশ্চেন আছে? And if you have any query, if you have any doubt, you can post that in the group as well. আমি ভয়েস রেকর্ড করে পাঠিয়ে দিতে পারি বা স্ক্রিবল করে আনসার করতে পারি, বা নেক্সট ক্লাসেও আমি আনসার করতে পারি, মানে ক্লারিফাই করার চেষ্টা করতে পারি। ঠিক আছে, তাহলে নেক্সট ক্লাসে আমরা এখান থেকে স্টার্ট করব। কত হয়েছে? 16. So should we end the meeting?
Yes, sir.
আচ্ছা, নেক্সট ক্লাস কবে করবে তাহলে আমাকে জানিয়ে দিও তোমরা।
আচ্ছা, ওকে।
এই 6টা থেকে শিডিউল করো, at least 2 ঘন্টা শিডিউল করো, uninterrupted.
Okay.
Thank you.
Thank you.
Thank you, ma'am.